Welcome back. Now that we've talked extensively about many of the features of these functions, and particularly of their graphs, we are going to actually graph one of these functions. So I would like to graph f of x equals 3x over x minus 1. Now this is a relatively small and fairly simple rational function, and this will give us an idea of the basic outline of the procedure. So the first thing that we would like to do is figure out the domain, figure out what x values we aren't even allowed to plug in. Now this function has already got its numerator and denominator as factored as they're going to be, so we can take the denominator and say, when is that equal to 0? Well, that happens when x equals 1, so let's avoid that x value. Alright. Now again, since this function is relatively simple, and we have it here in its factored form, we can see that step 2 is not going to change things very much. There's nothing that will cancel in this function. I have a factor of 3 and x in the numerator, and I have a factor of x minus 1 in the denominator. None of these have anything in common. So that is our function, and that's what we're going to base our the rest of our information off of. So I would like to do something we haven't done with these functions before. I would like to find the intercepts, and I'll start with the y-intercept. We've seen that that one's usually pretty easy. That involves plugging in 0 for x, letting x be 0, and evaluating the function. So that would be 3 times 0 over 0 minus 1. And our numerator is 0, our denominator is negative 1, so our y value is 0. So we see our y-intercept is the origin. And if I do something a little bit different, I want to find the x-intercept, or intercepts, possibly more than one. That is going to involve setting my function equal to 0. So when is 3x over x minus 1 equal to 0? And here I have a rational equation that I need to solve. So if I multiply both sides by the denominator, x minus 1, clear out my fractions, then I see on the left I have 0, and on the right I have 3x. So if I divide everything by 3, I see that this happens when x equals 0. So our x-intercept, and we only have one, is also the origin. Our x-intercept is our y-intercept, is the origin, and no place else. So our graph will only cross either axis at 0, 0. Alright, so we have both of our intercepts. Now I would like to find the asymptotes. So, looking at our function, I see that it is in reduced form, so I can find the vertical asymptote by setting the denominator equal to 0. Notice the connection between the vertical asymptote procedure and the domain procedure. Now, when we're finding the domain, we're figuring out what x are we not allowed to plug in. When we're finding our vertical asymptote, we are finding the equation of a line. So, x equals 1 is a vertical line at passing through every point with a coordinate, an x-coordinate of 1. And now we can look at the horizontal asymptote, see if we have one. Maybe we have an oblique asymptote. We'll find out. So I need to look at the leading terms. Here I have 3x over x. Those are my leading terms. I'm ignoring everything else. And I notice that they are the same degree. So that implies that my horizontal asymptote is going to be the ratio of the coefficients. So my numerator's coefficient is 3, and my denominator's coefficient, it's not really making itself known, but we have a 1. So our horizontal asymptote is the horizontal line y equals 3. So here I have condensed all of the information that we found so far. We are going to go ahead and start plotting all of this. Sketch out my axes and start including the information that we've found. Now I know my y-intercept and my x-intercept are both at 0, 0, so I know at least one point on my graph already. I have a vertical asymptote at x equals 1. So I will plot a vertical dotted line, and I'm using a dotted line now because my function doesn't actually include this line. This is just a constraint that's going to help me to graph my function itself. I also have a horizontal line at y equals 3. So if I come up to 3 and plot a horizontal line, that'll give us a good idea of where our graph can or cannot cross. Now, just to check and see if our function does cross our horizontal asymptote, remember that can happen, I will set my function equal to that y value. I'll set the two equal to each other and see if that works, see if there's an x value that makes that happen. Does our function cross its horizontal asymptote? Now I have to solve this rational equation, and I think the easiest way to do that will be to clear the fractions by multiplying by the least common denominator. So on the left I get 3x minus 3, and on the right my denominator cancels out and I just get 3x. Now if I try to solve this equation for x, maybe trying to get all of my x's on the right, I subtract 3x, I see that my equation results in a lie, in a falsehood. So since negative 3 is never 0, this is kind of like with those systems of equations type problems, the conclusion that I started from, that my function can never be equal to its horizontal asymptote, led me to a contradiction. So we don't ever cross. Okay, so now I'll plot a couple of additional points between my x-intercepts and my asymptote, my vertical asymptote, just to get the lay of the land, figure out roughly the shape of my function, and then I will graph it adhering to the information that we have so far. So some x values that we might choose. Well, we already know what happens when x equals 0. So I could try x equals a half, something halfway between my x-intercept and my vertical asymptote. So my function would be 3 times 1/2 over 1/2 minus 1. So that's 3/2 over negative 1/2. And I can keep change flip. That's 3/2 times negative 2 over 1. So my function's value is negative 3. So the point 1/2 negative 3 will lie on my graph, and I can plot that right about there. Maybe something to the left, just to kind of see what the overall shape of our function is to the left of the y-axis. If I plug in negative 1, then my function is 3 times negative 1 over negative 1 minus 1, which is negative 3 over negative 2, or 3/2. So about 1.5. We'll plot that right about there. And now, using those pieces of information, along with the idea of the asymptote, I can start to see how this graph must look. It's going to get closer and closer to that vertical asymptote as we approach it from the left. And as our function goes off to the left, it's going to get closer and closer to its horizontal asymptote. That's what the definitions of vertical and horizontal asymptotes tell us. Now, I don't know exactly what's going on to the right of the vertical asymptote here. So if I plug in some x value in that neighborhood, perhaps x equals 2, something to the right of 1, then I'll see that my function's y value, the function evaluates as 3 times 2 over 2 minus 1, which is 6 over 1, which is just 6. So we actually have a point way up here, plot 6. Now just to see a little bit better what's going on, let me go out a little further. I'll plug in 3, so our function would take that in. So we get 3 times 3 over 3 minus 1, that's 9 over 2, so 4.5. So if I come out to 2, my function is at a height of 4.5. And just for good measure, we'll come out a little bit further, plug in 4. My function takes that, and 12 over 3 would evaluate to 4. So if I come all the way out to 3, my function is actually at a height of 4. And you can kind of start to see how the asymptotes are going to affect our picture on this side of the vertical asymptote. So it's almost like a piecewise function. You'll have different areas where your graph will be doing very different things. And you just need to supply enough additional information to really nail down what that behavior is. Now, as you get more practice with these, those asymptotes are going to be much more helpful. You'll start to get the feel for how functions act in between vertical asymptotes and how they interact with their horizontal asymptote. But for now, make sure you're using enough additional points to get your graph as accurate as possible.